So we are now starting on SL section 1.5. This will be a continuation of our Oxford course using the Oxford textbooks for the SL A&I Math curriculum. So section 1.5 is on the trigonometry of right-angled triangles and indirect measurement. By indirect measurement, we mean measuring one quantity by measuring something else. What are some examples of indirect measurement? Well, you can't measure, for example, the height of a building very easily. You can't take a ruler and measure the height of a building. But if I can measure how far away I am from the building, which maybe is an easier measurement to make because it doesn't require somehow elevating, and I can measure the angle from myself to the top of the building, I can indirectly measure the height of the building. Trigonometry, which is a very important subject in mathematics, starts with right triangles and eventually extends to non-right triangles. But this section is about the trigonometry of right-angled triangles. So we're only dealing with right triangles. Right triangles have two basic mathematical approaches. The first one, if I give you a right triangle and I label the two sides of the triangle by A and B, and I label the hypotenuse by C, then we have the amazing relationship that if I square each of the two sides and I add them, and I square the hypotenuse, I get the same thing. A squared plus B squared equals C squared. This formula holds for right triangles and right triangles only. It is called, hopefully you know this is called the Pythagorean theorem, named after Pythagoras, although it was most likely known prior to him. The Pythagorean theorem, A squared plus B squared equals C squared. Is there a formula for non-right triangles? The answer is yes. It's called the law of cosines. What is cosine? Well, we'll get to that in a second. What is the law of cosines? We'll get to that much later. But for now, we have the Pythagorean theorem. It relates the three sides of a right-angled triangle. So immediately, I can solve something like the following. We have a right triangle here. The picture is shown. In the picture, it labels the bottom left corner here as angle A, the bottom right as angle B, and the top left as angle C. Tells me that we have 90 degrees. And it also tells me that line segment AC is 7 centimeters and line segment BC is 15 centimeters. And the question says, calculate the length of line segment AB in the right-angled triangle ABC, where CB equals 15 centimeters and AC equals 7 centimeters. So the information is provided. So when you're using the Pythagorean theorem, the one mistake I see people make is always assuming that the unknown, which you can label by whatever you want, we'll call it X, is always on the equal unknown squared side of the Pythagorean theorem, but it's not. The hypotenuse must be on the equal C squared side. So we have here is the currently unknown X squared plus 7 squared equals the hypotenuse, which is 15 squared. 7 squared is 49, 15 squared is 225. So X squared plus 49 equals 225. Subtract 49 on both sides. X squared equals 176. And therefore, what is the square root of 176? What is the x is approximately equal to 13.3. What are the units? Oh, centimeters. And to three significant figures, we have x equals 13.3 centimeters. I usually write approximately when I'm approximating, but the IB, when you round to three sig figs, they just say x equals 13.3 centimeters to three significant figures. Pretty straightforward. Also, you should know that the converse of the Pythagorean theorem is also true. So not only can you say, if it's a right triangle, then a squared plus b squared equals c squared, but if I give you a right triangle, if I give you three sides of a triangle, and I say, do these three sides form a right triangle? You can also check and say, well, does a squared plus b squared equal c squared? If so, it's a right triangle. If not, it's not. It actually goes both ways. So we can do the following example. We have a triangle, and we have a side of 6 centimeters, a side of 8 centimeters, and a side of 9 centimeters. And the question is, determine whether or not a triangle with these three sides is a right-angled triangle. And that's just checking whether a squared plus b squared equals c squared. But the first question you might ask is, well, which is a, which is b, which is c? So if it's not a right triangle, then ABC is irrelevant. Call everything whatever you want to call it. But if it is a right triangle, then C must be the hypotenuse. And the hypotenuse is the longest side of the triangle. So the only possible C is going to be the 9 centimeter one. A and B doesn't make a difference. So we'll call 6 centimeters A, we'll call 8 centimeters B. And the question is 6 squared plus a squared, is this equal to 9 squared? Question mark over the equal sign, because we're checking, we don't know. Well, 6 squared is 36, 8 squared is 64, 9 squared, still not sure, so still with a question mark. 9 squared is 81, 36 plus 64 is 100. 100 is not equal to 81. So the answer is a straight up no. This is not a right triangle, not a right triangle. Is it a valid triangle? Sure. 6, 8, 9, that is a perfectly valid structure, right? I can't have a triangle of sides 1, 1, and 100. So not every three sides automatically makes a triangle. How do you know? Well, if one side's 100 and then you have these little flippers on the end of side 1, right? There's no way these guys can meet. So there are restrictions on what three sides can form a triangle, but 6, 8, and 9 does. It's just not a right triangle. Another example. Sam's vegetable garden is a triangle. Now, I don't know if it's a right triangle, so I'm not going to draw anything yet. His plan shows that the plot is a right angle triangle. Well, that changes everything, and now I do have a right triangle. So I have a right triangled plot. Sam measures the sides of his vegetable garden as 17 meters, 144 meters, and 145 meters. So two things. First, notice this is not drawn to scale. Okay, 144 and 17 should not be in the same vicinity. That's okay, because the math will give me the answer. I don't have to worry about the picture. If you are concerned, you can always draw a better picture that would look something more like this. Even this is not quite to scale, but it doesn't really make a difference unless there's a lot going on graphically and you really need accuracy. And if that happens as you're working through a problem, certainly redraw the triangle. I don't foresee that happening here. So let's see what happens. Show that the plot is indeed a right angled triangle. I don't even need to draw the triangle, to be honest. I just need to check. Is 17 squared plus 144 squared, is this equal to 145 squared? We're just checking whether or not it satisfies the Pythagorean theorem. Well, 17 squared is 289. And 144 squared is 20,736. And we're checking whether this equals 145 squared, which is 21,025. And if you take 20,736 and add it to 289, you do in fact get 21,025. So the answer here is yes. It is a, that was a horrible right triangle. It is a, let's move this over a little bit so I have some room. It is a right triangle. Hopefully that makes sense. Very, very straightforward. This leads us into exercise 1G. As always, you should be stopping after I read each question, doing it yourself, and then checking the answer. So question number 1. Find the length of the unknown side in each of the following right triangles. Round your answers to 1 decimal place. Okay, so A, here's my right triangle. Oops. It gives me 13 meters. It gives me 12.2 meters, and it calls this W. Pause, solve, check. So 13 squared plus 12.2 squared is equal to W squared. Do not just square root both sides and write it like this. This is utter nonsense. This is not true. Bad. This is horrible. I see it so often. It's just bleh. When you have a plus sign inside of a square root, you cannot split the square root into 2 pieces. Cannot be done. You might say, why not? It sounds reasonable. Sure, it sounds reasonable, but let's just see if it works or not. What's the square root of 4 plus 4? Well, that's the same thing as the square root of 8, because 4 plus 4 is 8, and the square root of 8 is 2 square root of 2. Well, if I split this up into the square root of 4 plus the square root of 4, that gives me 2 plus 2, which is 4, and those are not the same thing. So you just can't do it. It's this step right here that you're not allowed to do, because everything else makes sense. You cannot split up a radical when there's a plus or minus sign inside. How do I do it? Well, easily. 13 squared plus 12.2 squared, that just gives me 317.84 is equal to W squared. I'm going to get rid of these radical signs for now. And then take the square root of both sides. So the square root of 317.84 is 17.828 dot, dot, dot. And because we're rounding, as the instructions say, to 1 decimal place, W equals 17.8. And then we go back and look at the units, and we make sure that our answer is in the correct units, which is meters. Part B, another right triangle. This one they drew a different way, but it doesn't change the fact that it's just right triangle. 9.7 millimeters is the hypotenuse. 6.1 millimeters is the base, and they're calling this side B, and they say solve for B. Pause, solve, check. And here the unknown is on the A squared plus B squared side. 6.1 squared plus B squared equals 9.7 squared. 6.1 squared is 37.21. 9.7 squared is 94.09. So if I subtract 37.21 on both sides, I get B squared equals 56.88. And then if I solve for B by taking the square root of both sides, I get 7.541 dot, dot, dot. So rounding to 1 decimal place, 7.5, and my units are millimeters. C, another right triangle. Very thorough. 4 questions. 7.5 millimeters, 3.5 millimeters. This one, we're looking for A. Pause, solve, check. A squared plus 3.5 squared equals 7.5 squared. 7.5 squared minus 3.5 squared. In this case, I'm doing it a little differently. I'm first subtracting before squaring. In the last example, I first squared and then subtracted. Who cares? A squared equals 44. Take the square root of both sides. A equals 6.63 dot, dot, dot. They want 1 decimal place, so A is equal to 6.6. What are my units? millimeters. And finally, we have D, another right triangle. This one, the hypotenuse, 14 millimeters. This base here, 9.5 millimeters. Calling this C. Ooh, they're trying to trick you. They're calling it C, but the C in the Pythagorean theorem is the hypotenuse. Well, they're just letters. If you don't want to use A, B, and C, just say one side squared plus the other side squared equals the hypotenuse squared. So we have 9.5 squared plus C squared equals 14 squared. So if I do 14 squared, which is 196, and I subtract 9.5 squared, this gives me overall 105.75. Square root both sides. C equals 10.28, dot, dot, dot. So to 1 decimal point, 10.3. What are my units? Millimeters. So that's question number 1. 4 parts. Now, question number 2. Determine whether or not the triangles with the following sides are right-angled triangles. Okay, well, we know how to do that. This one, we have 9 centimeters, 40 centimeters, 41 centimeters. So, as always, pause, solve, check. We want to see if it satisfies a squared plus b squared equals c squared. If it does, c has to be the longest side. So 9 squared plus 40 squared gives us 1681. 41 squared gives us 1681. So yes. B, 10 meters, 24 meters, 26 meters. Let's do the same thing. Pause, solve, check. 26 has to be the hypotenuse. So 10 squared plus 24 squared is 676. 20 squared is also 676. That works too. C, 10, 10, square root 200. This one is a unitless triangle. We don't know the units. We don't care what the units are. There's an implicit units going on behind the scenes, but they just don't play a role in the problem. Again, a squared plus b squared has to equal c squared. In this case, square root of 200 has to be c. So 10 squared is 100. 10 squared is another 100. So 100 plus 100 is 200. And the square root of 200 squared is 200. So I don't even need a calculator for that one. And we see that that one works as well. For D, we have 11.2, 7.5, and 8.3. Pause, solve, check. So 11.2 would have to be the hypotenuse. So 7.5 squared plus 8.3 squared, that's 125.14. 11.2 squared is 125.44. Oh, they're so close, but off by 0.3. I don't care what you're off by. If you're off, you're off. It's not a right triangle. So that takes us to question number 3. Question number 3 is a fun-looking problem. And it has this diagram here that is not going to be the easiest to draw. So I'll do my best. We have a right triangle here of sides length 1 and length 1. Then it forms a right triangle here. And that part is of length 1. Then it forms a right triangle here. And that part is length 1. Then it forms a right triangle here. And that part is length 1. And it keeps doing this all the way around the circle. It actually draws them all, and I just don't have the time for that. So I'm going to move this one out of the way, put it here. And it eventually gets to around here, which is the last right triangle that it forms. And again, this is length 1, and it calls this X. Now we're gonna have to know exactly how many there are for part D of this problem, but let's start with part A. So first it says the following. The spiral in the figure is made by starting with a right angled triangle with both legs of length 1. That's the very first one that we drew. It's got a 1 and a 1. Oh, and it's a right angled triangle. So let's make sure we have that. So part A says, find the hypotenuse of the first triangle. Pause, solve. 1 squared plus 1 squared equals hypotenuse squared. 1 plus 1 is the hypotenuse squared. 2 is the hypotenuse squared. Oh, it must be the square root of 2. So I'm going to label this guy right here. That's the square root of 2. So that was part A. B. Then the second right angle triangle is built with one leg measuring 1 unit and the other leg being the hypotenuse of the first triangle. So we have a square root of 2, 1, and now we have a new hypotenuse. And the problem says, find the hypotenuse of this second triangle. So let's pause and do that. Square root of 2 squared is 2 plus 1 squared, that's 1. 2 plus 1 is 3. Oh, that's going to be the square root of 3. So the next one is a little longer, and it's the square root of 3. Then we go to C. It says a third right angle triangle is built on the second triangle's hypotenuse, again with the other leg measuring 1 unit. So now square root of 3, 1. Find the hypotenuse of the third triangle. Well, pause, solve. Square root of 3, 3 plus 1. Square root of 3 squared is 3, 1 squared is 1. So I get the square root of 4. Now I could simplify it to 2, but it's actually a little better in the form square root of 4 so that you can see the pattern. The pattern is, and seems to be, that every time we get to the next triangle, the hypotenuse increases, well, the value inside the radical increases by 1. So 1 squared, well, 1, which is technically also, just throw it here for pattern's sake. This one right here is the square root of 1. It's 1, but it's also the square root of 1. So the square root of 1, square root of 2, square root of 3, square root of 4, and so on. So now part D says, the process is continued in the same fashion, and the hypotenuse of the final triangle is denoted by x. Find the length of x. So now we just got to count how many triangles. So if you don't have the book and you can't follow inside, I'm not going to draw this whole thing. It's just too time consuming. I'm just going to count how many triangles we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 triangles. And the 15th triangle, we're starting with there. That's the hypotenuse of the first triangle, square root of 2, which means the number inside the radical is always 1 more than which triangle it is. First triangle, square root of 2. Second triangle, square root of 3. Third triangle, square root of 4. 15th triangle, square root of 16. And therefore, x is equal to 4. Kind of a fun problem. And then finally, we have question number 4. It says a right angle triangle. Oh, stop, draw a right angle triangle. Draw a better right angle triangle. There we go. A right angle triangle has a hypotenuse of 8.2 centimeters. So let's label that. And another side length of 4.3 centimeters, not drawn to scale, but let's label that. Draw a diagram. Okay, gave that one to you. Then it says calculate the area of the triangle and give your answer correct to 1 decimal place. So we want the area. Of course, to do this, we need the formula for the area of a triangle. Well, there are many formulas, no, not many. There's a bunch of formulas for the area of a triangle. Others that you're going to learn later, which are actually somewhat more useful in different situations. But the most basic one that we know should be, and this is on your formula sheet in your formula booklet, 1/2 base times height for the area of a triangle. The base we have, it's 4.3 centimeters. But we need a height. So pause if you haven't already to find the height. Well, the height is just going to be the third side, or the second side, hypotenuse 2 sides. Pythagorean theorem. 4.3 squared plus the currently unknown h squared equals 8.2 squared. 8.2 squared minus 4.3 squared. We get h squared equals 48.75. Take the square root. H is equal to 6.98 ... Now you might say, oh, that means to one decimal place, h equals 7.0. And yes, you're right. To one decimal place, h is equal to 7.0. However, we're not looking for h. We're looking for the area. And we don't round until we're done with the problem. So when I plug in this h into my area formula, I'm going to keep all decimals. So I'm going to immediately multiply by b, which is 4.3. And then by 1/2, which is the same thing as multiplying by 0.5, or dividing by 2, it's all the same. And I get that the area is 15.0115. So to one decimal place, the area is 15.0, and my units are square centimeters. Just curious, had I rounded h to 7.0, multiplied by 4.3, and then divided by 2, I actually would have gotten 15.1 square centimeters. So yes, it is important not to round until you're done with the problem, or you will not get the value that the IB is expecting, and therefore you will not get it correct. So that's the first half of this lesson on right angle triangles, and that's using the Pythagorean theorem. The Pythagorean theorem is a relationship between the three sides of a right triangle. But it makes no reference to the angles themselves, other than the fact that one of the angles has to be 90 degrees. The other relationship between the sides also connects them to the angles. This is more trigonometry proper. The Pythagorean theorem is usually learned much prior to trigonometry, so it's not really part of trigonometry, other than the fact that it's requires a triangle. Well, I guess that makes it part of trigonometry, but usually it's still taught way earlier. And the basis for what we're going to do next is the following. If I make a right triangle, and I give this angle here, I call it, let's say, theta, angle theta, Greek letter theta. Actually, I think it's pronounced theta, but whatever. If I make another right triangle with the same angle, and I'll try to do a better job. Let's make these. And okay, not horrible. But I'll make a second right triangle with the same angles. And I'm going to label the initial angle as adjacent 1, opposite 1, and hypotenuse 1. And then I'm going to label the second adjacent by A2, opposite 2, and hypotenuse, or H2. Then something pretty interesting occurs here, which is that the ratio of opposite 1 to adjacent 1 and the ratio of opposite 2 to adjacent 2 are the same. Similarly, the ratio of opposite 1 to hypotenuse 1 is the same as the ratio of opposite 2 to hypotenuse 2. And the ratio of adjacent 1 to hypotenuse 1 is the same as the ratio of adjacent 2 to hypotenuse 2. This comes from similarity of triangles. When two triangles are similar, or two polygons in general are similar, or two shapes are similar, then the ratios of their sides are constant, are the same. In other words, these ratios don't actually depend on the sides. They only depend upon the angle. If I know the angle, I immediately know the ratio of the sides. So that these ratios, being dependent upon the angle, are functions of the angle and only of the angle. And these three functions have names. The first one is called the tangent function, and we'll usually say tangent of theta, or tan theta. The second one is the sine function, and we'll usually say sine theta. And the last one is the cosine function, and we'll usually say cosine theta. And I'm not the biggest fan of mnemonics, but there is one mnemonic that I like. SOHCAHTOA, very famous. SOHCAHTOA. It's an okay mnemonic in my book because it's a definition. You're not memorizing something in place of understanding. You're memorizing something because it's defined that way. And this means that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And finally, we have tangent is opposite over adjacent. Those are three definitions. And what they allow us to do is connect an angle to two sides. So that if I have two of them, I can find the last one. Anytime I have two sides, I can find an angle, or if I have an angle on a side, I can find another side. Let's show how these are put into practice by doing a few examples, and then you'll do a few exercises. So let's start with the following example. I give you a right angle triangle, and remember, as before, SOHCAHTOA only holds for right triangles. It is not valid for non-right triangles. Now, eventually in trigonometry, we deal with angles that can't be in a right triangle, like, for example, 100 degrees or negative 12 degrees. And we want sine and we want cosine and we want tangent of those, and we can do so. But for now, sine, cosine, and tangent are limited to being between 0 and 90 degrees, non-inclusive, because you can't have 0 degrees, you won't have a right triangle, and you can't have another 90-degree angle, you can't have a right triangle. This angle here, theta, this angle must be between 0 and 90, non-inclusive, otherwise SOHCAHTOA does not work. Later, we'll worry about what if it's not. So, it says we have 4 centimeters, we have 3 centimeters, and we have 5 centimeters. Now, it didn't really have to give us all 3 sides, because if it gave us 2 of the 3 sides, I can use a Pythagorean theorem to find a third. But we're focusing here on the angle. And it says find the size of angle A. So they're not using the Greek letter theta. They're using, they're calling this point A, and then calling this here angle A. They're making a distinction between the point and the angle at the point, which I'm okay with. I'm okay with. It's a little, overkill, but I'm never against precision like that. The differentiation between the point and the angle. So I'm going to go with it. We have angle A. They use a caret, a little hat symbol over the angle, and then they have point A, and they don't. But if you're writing quickly and you say sine of A and you don't include the hat, I forgive you. So it says, find the size of angle A. Now we can do so in 3 ways. I can use sine and say, what is the sine of angle A? Well, it's opposite. Opposite angle A is 3 centimeters. Adjacent to angle A is 4 centimeters, and hypotenuse is 5. Opposite the angle, adjacent to the angle, and of course the hypotenuse is always the longest side. So how is sine defined? Sine is opposite over hypotenuse, so sine of angle A is 3/5. Congratulations, that doesn't tell me what A is. I don't want sine of A, I want A. So what we're gonna do is we're gonna go take out our calculator, and we're gonna look for the button that says sine, and it looks like a -1 power. It's not a -1 power, it's an inverse, sine inverse of 3/5. And you want to make sure that you are in degree mode in your calculator, not radian mode. Hit the mode button, go down until you see the radians and degrees, put it in degrees, quit out, and then we're going to do sine inverse of 3/5. And since it does not give us any number of sig figs or decimal places, we will do the standard 3 sig figs and get 36.9 degrees. And you must include the degree symbol, otherwise it is not correct. Not having degree symbols tells me that you're dealing in radians. If you want to be in degrees, use the symbol. Now, what if I didn't want to use sine? What if I wanted to use cosine? Well, cosine is defined as adjacent over hypotenuse, 4 over 5. How would I find A if I used cosine? Well, I would use the cosine inverse button. And if I use the cosine inverse button of 4/5, magically, I also get 36.9 degrees. And what if I wanted to use tangent? Well, tangent is opposite over adjacent, so 3 over 4. How do I get A from knowing tangent of A? Well, how about the tangent inverse button? Tangent inverse of 3 over 4. And once again, I get 36.9 degrees. So this is an example where you could have used any one of the three. Sometimes you have to use one. Or you should use one. This time, any one of the three would have been equally valid because you have all three sides. Let's take a look at the next one. Shown here is the right angle triangle FGH. So this down here is point F. This over here by the 90-degree angle is point G, and this is point H. FH, the hypotenuse is 14 centimeters. Let's label that. FHG, angle FHG is 52 degrees. FHG, hold on. Okay, so we have this right angle triangle, FGH. We have a 52-degree angle is angle FHG. So which angle is FHG? Well, start at F, go to H, go to G, and it's that angle. So FHG is this angle up here, 52 degrees. And it says find the length of side GH. So we'll give this a name, we'll call it X. And our goal is to find the length of side GH. Now the question is, we can't use the Pythagorean theorem because we don't have the other side. So the only other recourse is either sine, cosine, or tangent, as far as we've learned. So the question is, which one is appropriate? So we have the angle 52 degrees. Which three sides between opposite, adjacent, and hypotenuse are relevant to this problem? Well, the hypotenuse is 14 centimeters. We're going to need that. And we're looking for the side adjacent to the angle. So we need adjacent and hypotenuse. Which of my three trigonometric functions, sine, cosine, or tangent, deals with adjacent and hypotenuse? That's the cosine. So cosine of 52 degrees is equal to the adjacent side, which is x, over the hypotenuse, which is 14. And here we have a equation involving the variable x. It's the only unknown. So we can solve by what? By cross multiplying. Well, what exactly is cosine of 52 degrees? I don't know. I mean, I know approximately what it is, but if I want exact, go to your calculator. Cosine of 52 degrees, and you multiply that by 14. X is equal to 14 cosine of 52 degrees. It does not say how many sig figs, so we are going to go to 3 sig figs, and we get 8.619 to 3 sig figs. That is 8.62. And then I check my units, and we're going to have units of centimeters. So 8.62 centimeters. Let's do another example. Emma is standing in front of a big tree. So here's my big tree. It's a horrible looking, it's not, I can't even pretend that's a tree. So let's try this again. So there's the base, and here is the tree. Okay, and Emma is standing in front of the tree. So here's Emma. She's not levitating. She's just, how do I can lower it. Okay, so there's Emma. She's standing in front of the big tree. She measures her distance from the tree as AB equals 15 meters. Now, the picture in the book has this as A, and this point here is B. And it draws a horizontal line from her eye to the tree. And then she also measures the top of the tree down to her eye. This is the top of the tree, point C. And we have angle A hat is 40 degrees. So she measures 40 degrees as the angle, and she measures 15 meters as how far she is from the tree. It says find the length BC. Well, you're looking for this length here, BC, which, by the way, is not the height of the tree. It's rather the height of the tree from her eye level and up. So the question is, we can't use the Pythagorean theorem here. I only have one side. Notice, by the way, that the 15 meters is also the same. 15 meters is up here. They are parallel line segments, one on top of the other. But I don't have the other two sides, so I can't use the Pythagorean theorem, but I have an angle. So it's either sine, cosine, or tangent. Well, which sides are relevant? I don't care about the hypotenuse in this problem. I don't even care what it is. Adjacent's 15, opposite is what I'm looking for. Which trig function uses adjacent and opposite? Tangent. So tangent of 40 degrees equals opposite. We don't know it. We'll call it x over adjacent, which is 15. X equals 15 tangent of 40 degrees. I don't know what tangent of 40 degrees. It's a little less than 1. It's 0.839 dot, 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 but I'm going to multiply by 15 before approximating. 12.586 dot, dot, dot. And because there's no restrictions, we're going to use 3 sig figs. And I get 12.6, and that's going to be in meters, 12.6 meters. And then it says, state what other information Emma needs in order to calculate the height of the tree. So what other information does she need? Well, if you think about it, the only thing missing is this height right here, which is equivalent to from ground level to her eyes. Now, a person's eyes are basically near the top of your head. When you're dealing with 12.6 meters, if you're off by a couple centimeters, not the biggest deal, but you can also take that into account if you know eyes to top of your head. Essentially what you need is her height. You take her height, maybe subtract a few centimeters, add it to 12.6 meters, and that will give you the height of the tree. So hopefully that makes lots and lots and lots of sense. Let's now jump ahead to exercise 1H. As always, pause, solve, check. So question number 1. Determine the length of the unknown sides for each of the right angle triangles shown below. So we have a right angle triangle here. And this angle down here is 61.2 degrees. And they call this Y, they call this Z, and this is 9 centimeters. So cannot use the Pythagorean theorem because I do not know two sides. So my only other recourse is to use some trigonometry. What do I want to use? Well, it depends on what you want to solve for first, Y or Z. If you want to solve for Y first, then I'd be using opposite and hypotenuse, so sine is appropriate. If you want to solve for Z first, then I'd be using adjacent and hypotenuse, cosine is appropriate. I'll do Y. Sine of 61.2 degrees equals opposite over hypotenuse. So if I do sine of 61.2 and I multiply that by 9, I get Y to 3 sig figs is 7.89, and the units are centimeters. Now I want to find Z, and I can do it in 2 ways. One way is to say, well, now I do have 2 sides of my triangle, so I can use the Pythagorean theorem. Z squared plus Y squared equals 9 squared. Solve for Z. Nothing wrong with that. But since we're trying to get practice with trigonometry, I'll use cosine. Cosine of 61.2 degrees equals adjacent over hypotenuse. Cosine 61.2 times 9. That means to 3 sig figs, Z is equal to 4.34 centimeters. If you did use the Pythagorean theorem, Hopefully you got the same thing, and hopefully you remembered that even though we wrote down y equals 7.89, when I use it to do further calculations, I use all of the decimal points in y, so I don't do any rounding till the end. In fact, I'm just curious, what would happen if I didn't round? 7.89 squared without all those decimal places, and then I do 81 minus that, and then I square root that. That would have given me 4.33. Oh, look at that. It would have been wrong. 4.33, not 4.34. Part B. Another right triangle. This one's shaped a little differently. This is 10.2, no units. This is 34 degrees. Label this as X, and label this as Z. Same basic idea. You have to decide what to go for first. Pause, solve, check. Let's go for X first. If I go for X first, X is adjacent, 10.2 is opposite. What uses adjacent and opposite? Tangent. So tangent of 34 degrees equals opposite, which is 10.2 over X. This comes up often enough that you should know immediately what to do. Whenever you have two fractions that are equal to each other, and tangent 34 degrees can be thought of as tangent 34 degrees over 1, you can flip the top left and the bottom right, assuming nothing zero, you can flip them. So the X and the tangent 34 degrees just change places because that's how you cross multiply. A times B equals C times D. Of course, you can go ahead and cross multiply and eventually get to the same result. 10.2 divided by tangent 34 on my calculator to 3 sig figs gives me X is equal to 15.1, and there are no units. Again, now that I have X, I can use the Pythagorean theorem, or I can say, well, now I want to find Z. I'll use trigonometry because that's what this section is all about. 10.2 is opposite. I want Z. I'll use sine. Of course, you can say, well, I know X is 15.1 now. Why can't I use cosine? And the answer is you can. Nothing wrong with that. Just make sure you don't round to the end. But I'm going to use sine. That way I don't have to worry about rounding, because if you look at my equation here, there's nothing to round. This is an exact equation. Z equals to 10.2 over exactly sine of 34 degrees. If I would use either the Pythagorean theorem, or if I were to use X and use cosine, I'd be using a rounding number. And why use a rounding number if you don't have to? So when I do Z to 3 sig figs, I get 18.2. C. Another right triangle, again, shaped a little differently, but still a right triangle. This is X, this angle here, 66.4 degrees. This is Y, and we have 21.3. No Pythagorean theorem, at least not yet. So what am I going to use? Well, let's see. Which side do I have? I have the opposite, and I want adjacent, and I want hypotenuse. I'll go for adjacent first, X. Opposite, adjacent, oh, that's tangent. So tangent of 66.4 degrees equals 21.3 over X. Just like before, flip the X and the tangent. So X equals 21.3 over tangent of 66.4 degrees. 21.3 divided by tangent 66.4 to 3 sig figs gives me 9.31. And again, there are no units. Now that I have X, this time let's use the Pythagorean theorem just to throw it in, mix it up a little bit. So 9.31 squared plus 21.3 squared equals Y squared. Don't forget, even though I'm writing 9.31 on my paper, when it comes to actually doing it in my math, I use all decimal places. So it's 9.3057411186 squared plus 21.3 squared, and then square root that, and I get Y equals 23.2 to 3 significant figures. Let's change up the colors and go question number 2. A ladder KM is 8.5 meters long, and it leans against a wall. So we have this ladder. Here's the wall. Here's the ladder. And the ladder is KM, and that's L. And they tell me the ladder is 8.5 meters long. It leans against the wall, so that angle LKM, that's this one down here, is 30 degrees. And triangle KLM is a right angle triangle. KLM, KL, that's just over here. Okay, so that's just the information that they give us. Part A, find the distance KL. How far am I from the wall? Well, I don't have two sides, so I can't use the Pythagorean theorem. Again, pause, solve, check. So what can we do here? Well, we have trigonometry. It is a right triangle. I have the hypotenuse. I want the adjacent. Which one uses those? Oh, that's cosine. So cosine of 30 degrees is adjacent. I don't know it. Let's call it x, is adjacent over hypotenuse. In this case, I don't have to flip. I just have to cross multiply. 8 equals 8.5 cosine of 30 degrees. Now, cosine 30 degrees is an important one to know. But at this point, you have your calculator, so who cares? 8.5 times cosine of 30 degrees. And this gives me, again, three significant figures. It gives me 7.36. 7.36 what? 7.36 meters. B. Find how far up the wall the ladder reaches. Well, two options, Pythagorean theorem or back to trigonometry. Again, let's focus on the trig. So hypotenuse, I know. Opposite, I want. Opposite hypotenuse, which one's that? Oh, that's sine. So sine of 30 degrees equals, we'll call this y, equals opposite over hypotenuse. So y equals 8.5 sine of 30 degrees. And on your calculator, you get an exact 4.25 meters because sine 30 degrees is equal to a half, for reasons that aren't important right now, but it's one of those things that we should certainly know. So the ladder reaches up 4.25 meters. C. The instructions for use of the ladder state that it should not lean against the wall at more than 55 degrees. Find the maximum height up the wall that the ladder can reach. So if you think about it, the closer the base of the ladder is to the wall, the higher up the wall that it reaches, but the steeper the angle. So when moving it closer, it's gonna go higher. So I'm gonna draw a new right triangle. This is still the same wall as it was before, but now we have an 8.5 meter long ladder at 55 degrees. It should reach higher up the wall. So we'll call this y again. Well, let's not use the same y. We'll call it z now. And the question is, before it was 4.2 meters, but now I moved it closer, it's steeper, it should go higher. What's it gonna be? Well, I can't use the Pythagorean theorem. I don't have two of the three sides. So what do I have? I'm looking for opposite. I have hypotenuse, opposite hypotenuse. That's sine. So sine of 55 degrees equals opposite over hypotenuse. So if I multiply 8.5 times sine of 55, this gives me to three sig figs, 6.96 meters. That's the highest it can possibly get to. And finally, the last question in the section. Question, let's go this color, whatever it is. Question 3. It says a hiker whose eye is 1.6 meters above the ground. Okay, so here's the ground. And here is our hiker whose eye is 1.6 meters above the ground, stands 50 meters from the base of a vertical cliff. So here is the vertical cliff, and the hiker stands 50 meters away from the base. The angle between the line connecting her eye and the top of the cliff, that's the line connecting her eye and the top of the cliff, and a horizontal line is 58 degrees. Again, the angle between the line connecting her eye and the top of the cliff and the horizontal, that's 58 degrees. A, draw a diagram representing the situation. So I did that one for you. But B, it says find the height of the cliff. As always, pause, solve, check. So what is the height of the cliff? Well, the height of the cliff has two parts. It's the bottom, which is 1.6 meters, and then this part here, which we'll just call X. X is part of a right triangle where I have the adjacent to my angle, but I'm missing the opposite. Adjacent, opposite, that's tangent. So tangent of 58 degrees equals opposite over adjacent. So X is 50 times tangent 58 degrees. That's 80.0167, But I want the height of the cliff. The height of the cliff is not X. The height of the cliff is X plus 1.6. So I'm going to add 1.6 to that and then take that to 3 sig figs. I get 81.6 and one of my units, meters. So that takes us to the end of section 1.5. Next lecture will be on 1.6, which is the last section of chapter 1. And then that will be followed by going through all the exercises at the end of the chapter. So 2 more lectures on chapter 1, and then we can move into chapter 2. So hope to see you there. And if you have any questions, as always, feel free to leave a comment. And if you're in my class, you can always ask me in class. So talk to you guys later. Bye.